So I saw this presentation the first time this morning, so please bear with me if I stumble on the details. But I will show you how we verify and compare to ERA 5, and I think the added value to global reanalysis has been well established now by all the previous presentations, but you will see what we have found as well. So we haven't done so many case studies as Morten showed. We have mainly done statistical verification, and for that we use the verification tool available from Harmony, where we extract model data and the observations that's used in the model, and we use that to do statistical verification, where we compare the forecasts and analysis to the observations. Mostly conventional observations only. We do that to the surface and upper air data, and it's done for all the streams, for high-res and the EDA, but for the EDA we only do it for the control member, because we assume that the other members are comparable to the EDA member. It's slightly less quality, of course, since they are perturbed. And we do it seasonally, December, January, February, winter season, and we have a spring, summer, and then autumn seasons as well. And the CERRA land, as you heard, was done separately. We don't do that at SMHI or in the production. So here are a couple of examples how it might look like. This shows the error as a function of the forecast lead time. You have the upper two lines are the standard deviation, and the lower two lines are the bias or the systematic errors between the observation and model data. And you see that we have the CERRA in red and ERA 5 for the corresponding period in green. And this is for a spring period in 2019. We do long forecasts from our system at 12 and 0. So this is for the 12 and 0 forecast. We do 30-hour forecast lengths. For the high-res and for the EDA, we only do 6-hour forecast all the time. But you can see that for 10-meter wind, as in this example, we have a better standard deviation than ERA 5. The bias are about the same. For the high-res, for the EDA, it looks a little bit different for the bias. Better in the beginning, but then a little bit worse in the end. But the standard deviation is slightly better for CERRA, the number 0. We can also look at time series. Can be a bit messy, these plots. But the left plot there shows 2-meter temperature at 2 meters then. And you can see that the red dots, again, CERRA is in red. We are standard deviation slightly better than ERA 5 through all the period. The gray squares there are the number of cases. We don't have to care about those so much. But for the left, the right side shows the upper air at temperature at 500 hectopascals, and there you can see it is more similar to ERA 5. It's hard to say which one is actually the better there. But we can also look at the vertical profiles where we compare to radiosones. And this left side shows, let's see, I think it's geopotential for this period. 12, it's 0, 12, and 24-hour forecast, so it's a mixture of all forecast lengths. And here you can see that it's actually for the standard deviation, which is the right curves in the left plot for geopotential. It's very hard to beat ERA 5, because ERA 5 is a global reanalysis, and the geopotential is a large-scale parameter, which is so it's very hard to beat a global model, even though the resolution is slightly lower. It's very hard to beat it. It's happy to see that the systematic error is slightly better for our case, for CERRA in red. Temperature, a bit similar. They're more alike, because temperature is maybe more easy to beat the global model. But for geopotential, it's very hard to do that, or for higher levels. So it's more, it's already been said, for the small scale features at the surface or boundary layer that we have our full potential. We can also do map plots. If we discover some strange feature, we can look at the map and see where the biggest differences are. On the left, you have standard deviation for 2-meter temperature. Sorry, it's the bias for 2-meter temperature, and to the right you have bias for 2-meter temperature for ERA 5. And it's hard to say from this plot here that there are any differences, but maybe with some goodwill you can say that there are more yellow and light blue dots for CERRA and more dark red and dark blue for ERA 5, which would mean that we are closer to 0 in the bias than ERA 5. But it's hard to say. These are mainly for if we discover something that looks suspicious, you can look at these maps to see if there's some specific area or if we lose all the observations from some place or something like that. We can look at scatter plots. This compares the observed and the modeled parameters. Diagonal will be perfect, of course. And this is 2-meter temperature. CERRA again to the left and ERA 5 to the right. And I think it looks a bit like CERRA is a bit tighter to the diagonal, which is good compared to ERA 5. At the bottom here, the very low temperatures, we have some problems to represent those fully. But that's also the same case for ERA 5. So that's something we need to be aware of. Other verification tools or scores, you can look at the skill scores. There are different kind of measures. What's shown here is, as an example, is the Kuiper skill score. Closer to 1 is the better. And this is for 2-meter temperature again. And you can see that the red line CERRA is closer to 1, which is the perfect score would be 1, and we're quite close to that for CERRA. And the second one shows wind speed, I think 10-meter wind speed, and we're also closer to 1 than ERA 5, which is good. We have also a tool to monitor the use of observations, because we want to know that if some observation type is lost for some period, we can discover that quite quickly by looking at the plots coming out from this tool. And that basically visualizes the ODB, the observation database that is used by the model. You can get all kinds of statistics from that. But mainly what we look at in the quick glances are the number of observations on time series, where we can see that if something suddenly changes or happens, we can discover that and go into details then to see what has happened, why some observation type was missing. So this shows 2 examples. The left one shows satellite data from AMSU-A traveling on METOP A, I think METOP 2 is actually. And 2 different channels. You can see that there are more observations from one channel than from the other, but that's not sure of the details, but I think a few of the channels, they peak at different heights, and some channels we only use over land, and some channels only use over sea. So that's the reason why the different number of observations in those. And to the right, you see the SYNOP, the geopotential height from SYNOP stations, and that's quite stable. Differs a bit over the day. I'm not really sure why, but my guess is that since we add some local observations, those are probably not available for all observations hours. I'm not sure, but that is my guess, because SYNOP is usually measured every hour. So we should have the same number of observations, but it's something like 150 observations that some assimilation cycles are missing. But so these kind of things can be visible here if we want to investigate further. Some of the problems we might encounter with reanalysis was already a bit touched upon this morning, but there's some additional problems or things to be aware of for the regional reanalysis. The example here shows the number of observations for the UERRA period. It goes from 61 up until close to today. And you can see that the number of observations is constantly increasing, especially from something like 1990 or 2000, where we get more and more aircraft observations, and that those increase very rapidly by the end there. And that will, of course, influence the quality of the reanalysis. So it's not for certain that you have the same quality over the all 60 years, because the number of observations increase. Another thing for the regional reanalysis is that we have boundary conditions. We have models on the boundaries. And for UERRA, we had to switch in 1979, where we switched from ERA 40 to ERA interim. And you will see that that had a quite clear impact on the quality of the reanalysis. So what is shown here is the forecast differences between a 30-hour forecast and a 6-hour forecast, valid at the same time. And that gives an indication of the quality of the forecast, or how the forecast errors develop over these 30 hours. And you can see that in 1979, here we have a big drop, big increase in the quality. And that's where we switch from ERA 40 to ERA interim on the boundaries. And then you can see there's a slight trend in better and better quality from 1979 up until today. And that's because of the use of more and better observations. And yes, this will already been said, that adds value because it can resolve both topography and local variations of the forecasts or observations and such thing in the regional reanalysis with higher resolution. Yes, that was it. Yeah, thank you.